In this paper, we present a novel approach to address the pose control of soft robots using a manipulability-aware redundancy resolution method. The soft robotic arm in this paper is made of 3 sections: proximal, medial, and distal. Each section is equipped with 3 actuation units, evenly placed circumferentially. For larger stiffness, dual actuators are employed in each actuation unit of the distal and medial sections. A string rotary encoder is used to measure the elongation of each actuation unit. By pressurizing the actuation units, the robot deforms into complex shapes. We initially start by reviewing previous methods to derive the forward and differential kinematics. Then, we address the kinematic control by proposing a redundancy resolution algorithm that prioritizes position over orientation control. Additionally, the algorithm leverages manipulability awareness to switch gains and modes, enabling stable motion when the robot gets close to singular or near singular configurations. The hybrid serial parallel architecture and the absence of a wrist joint in the soft robot pose challenges in simultaneously controlling position and orientation. The coupled manipulability is heterogeneous and varies widely, indicating that the robot may face configurations with low manipulability, which could limit movement capabilities. Although position manipulability distribution is heterogeneous, the smaller variation in position manipulability and the absence of singularity suggest that coupled control is significantly more challenging than the position control. From our simulation studies, it is clear that our proposed method achieved the highest success rate with minimal deviation from the intended path and orientation. The integration of the weighted Jacobian for handling the joint limits, priority-based control, manipulability awareness, and gain scheduling significantly enhances the accuracy and smoothness of our algorithm. We implemented the proposed and comparative algorithms on our soft robot hardware to investigate their convergence behavior and accuracy in real-time implementations. In this section, we highlight the detrimental effects of high path and orientation deviations on convergence behavior and accuracy. The pose errors are calculated through a forward kinematics formulation with real-time measurements of actuator variables, isolating our implementation from kinematic uncertainties. Our proposed method achieved the desired position with a much faster convergence rate, subsequently reducing the orientation error through self-motion without impacting the primary task of position control and without any abrupt changes or deviations. As anticipated from simulation data, other methods, specifically CRR and WCC, exhibited deviations from a consistent decrease in position and orientation errors. These abrupt changes occur when the coupled manipulability was decreasing, highlighting the importance of adopting a priority-based control strategy in addressing this challenge. In the case of DRR, despite high manipulability in all 3 manipulability measures, the robot was unable to maintain the desired pose due to the high speed of the resulting motion, causing it to oscillate around the desired pose. To address the oscillatory and non-consistent motions of comparative approaches, their parameters have retuned. Additionally, a camera was used to close the feedback loop for both position and orientation errors, allowing us to evaluate the performance of algorithms under kinematic uncertainties. Again, our method demonstrated superior accuracy and convergence speed compared to the other methods. This slide shows an example of typical motions of all methods after retuning the comparative methods. Observations reveal that in methods incorporating a decoupling between position and orientation control, namely ours and DRR, the general behavior prioritizes achieving the target position, followed by managing the orientation through self-motion in the null space of the position task. In contrast, with other approaches, there is a noticeable trend of change in convergence even with retuning the parameters. Overall, our manipulability-aware redundancy resolution algorithm outperforms the compared methods in both position and orientation error convergence.